So in this video, we are going to look at the proofs for the compound angle formulas and some proofs for double angle formulas. So I'm going to start by proving the compound angle formula cosine A minus B, which is equal to cosine A times cosine B plus sine A times sine B. One way to prove this formula is to consider two angles in standard position with terminal arms of length 1, as shown in the picture below, angles A in red and angle B in green. So our first goal is to find the distance between points A, given here, and point B, given here. So notice the points for A and B. The x value is the cosine of the angle attached to that terminal arm, and then the y value is the sine attached to the angle of that terminal arm. So how did we get those coordinates? Well, let's look at a simple example. So imagine this is our point here. We'll call it x and y. We know the base is equal to x, the height is equal to y. And since we're dealing with a circle of length 1, the hypotenuse is equal to 1. So if we're focused on angle theta, first of all, we see that cosine of angle theta, which is equal to adjacent over hypotenuse, is x over 1. So the x coordinate is equal to cosine theta. And if we do the same thing with sine theta, we see sine theta is equal to opposite over hypotenuse, and therefore sine is equal to y. So if we want to find the distance between points A and B, we are going to use our distance formula. And our distance formula is based on Pythagorean's theorem, where the distance between 2 points squared is equal to delta x squared plus delta y squared. Alright, so let's use our formula. So distance squared, or in this case, the c value squared, because if we look at our line here, we called it c in our diagram. That's equal to the change in the x's. So if we go from point A to point B, our x values are cosine A and cosine B, all squared. And then our y values are sine A and sine B. Next, let's expand these quadratic expressions. So I get cos squared A minus 2 cosine A cosine B plus cosine squared B. And then for my second set of brackets, that is sine squared A minus 2 sine A sine B plus sine squared of B. Let's rearrange this a bit. Notice I have sine squared A and I have a cos squared A, which I'm going to put together. I also have a sine squared B plus a cos squared B. And then I still have left a 2 cos A cos B and a minus 2 sine A sine of B. Sine squared A plus cos squared A is one of our identities, and that is equal to 1. Same with sine squared B plus cos squared B. That is also equal to 1. So what I'm left with is 1 plus 1 is 2. I'm going to take a common factor out of the next two terms. And I have minus 2 cos A cos B minus or plus sine A sine B. And notice it's starting to look like our definition of cosine A minus B. So I'm going to stop there and call that equation number 2. Now let's look at it a different way. Let's use our cosine law. So again, if we're focused on this triangle here, the angle shown here we can see is A minus B. So remember, our cosine law states that c squared is equal to a squared plus b squared. And since we have a circle of radius 1, this will be 1 squared plus 1 squared minus 2 times 1 times 1 times cosine of the angle opposite side C, which in this example is A minus B. If we simplify this a bit, we get c squared is equal to 2 minus 2 cosine a minus b. And I'm going to call that equation 1. So recall that this is also c squared, so I'm going to sub equation 1 into equation 2. And now I have the following. 2 minus 2 cosine of a minus b is equal to 2 minus 2 bracket cosine a cosine of b plus sine a times sine of b. If I subtract 2 from both sides and then divide both sides by negative 2, I end up with the following equation. That cosine of angle A minus B is equal to the cosine of A cosine of B plus the sine of A and sine of angle B. And we've now proven our compound angle formula for cosine A minus B. And then using this formula, you can now prove some of the other compound angle formulas. But let's look at a proof for sine A plus B. So the proof for sine A plus B is going to involve our cosine A minus B formula, and I'm going to show you how. So I'm going to start with the left side of this equation. And what I can do is change this into a cosine function. And how can I do that? Well, let's look at this using a right triangle. For this right triangle, I can see that sine of theta is equal to b over c. Well, let's take a look at this angle here. Remember, in a right triangle, all the angles add up to pi. So the following two angles must add up to pi over 2, since we have pi over 2 taken up by the right angle. So theta plus alpha must equal pi over 2, or what we would say 90 degrees, because the other 90 degrees is taken up by the right angle. So alpha is actually equal to pi over 2 minus whatever theta is, or 90 minus theta. So let's look at what cosine is equal to in this example. So cosine of pi over 2 minus theta is equal to, well, if looking at this diagram, is equal to b over c, which tells us that the sine of theta is equal to the cosine of pi over 2 minus theta, if I put these two equations together. This is called the cofunction identity. So we're going to use that in this proof. So sine theta is equal to cosine pi over 2 minus theta. So using the cofunction identity, this would be the same as cosine of pi over 2 minus a plus b. All right, so let's rearrange this a bit. So this is the same thing as cosine pi over 2 minus a minus b, which is the same thing as cosine of pi over 2 minus a as one object minus b. So notice this now looks like our cosine a minus b formula, where this is a and this is b. So using the compound angle formula, I get cosine pi over 2 minus a cosine b plus sine pi over 2 minus a sine of b. And once again, notice I have my cofunction identities here. So we can rewrite those as sine of a, because sine of a is equal to cosine of pi over 2 minus a, and sine of pi over 2 minus a happens to equal cosine of a. And this proves that sine of a plus b is equal to sine of a times cos of b plus cos of a times sine of b. So these first two proofs, I wouldn't expect that you develop them yourself, but just take note of them. And with these two, you can now prove the rest of the compound angle formulas. And then with the compound angle formulas, you're going to prove the double angle formulas. So I'm going to help you with the first one. So I want to prove that cosine A plus B this time is equal to cosine A cosine B minus sine A sine B, using the compound angle formula for cosine A minus B. So how do I do that? So let's start off with the left side again. So cosine A plus B. Well, that's equivalent to the cosine of A minus negative B. Notice now, this is my A and this is my B for my compound angle formula for cosine A minus B. So now let's use the formula. So this will be cosine A times the cosine of whatever second angle is, in this case is negative B, plus the sine of A times the sine of negative B. Now what do we do? We're going to have to use the fact that the cosine function is even and the sine function is odd. So remember, if a function is even, so let's start with the cosine. So cosine theta is even. And if that's the case, that means that the cosine of negative theta is equal to the cosine of positive theta. And we also know that sine theta is odd. And what that means is that the sine of negative theta is equal to the negative of sine theta. So let's start with the first one. So cosine A times cosine of negative B. Well, since that's an even function, that's the same thing as the cosine of positive B. Okay, so we notice we changed that, the cosine of positive B. Plus the sine of A, and sine of negative B, since it's an odd function, is the same thing as negative sine of positive B. If we simplify, we get cosine A, cosine B, minus sine A, sine B. And we've now proven that cosine A plus B is equivalent to cosine A, cosine B, minus sine A, sine B. So we've proven our second compound angle formula. So using a similar idea, I'd like you to prove the compound angular formula for sine A minus B. And then for the tan A plus B, I'd like you to start with the left side, use the quotient identity, and then use your sine and cosine compound angle identities and see where you end up. And then once you've proven the tan A plus B, you should be able to prove the tan A minus B. And once you've done those three, I'd like you to prove the double angle formulas. If you have any questions, please let me know. But of course, try this yourself first. And good luck.